Hello, kiddos. So you have now developed some ability with adding vectors. All right. So let's say that you are given vectors x and y. Here are vectors x and y. Here's vector x. Here's vector y, and you want to define. I don't know if that's a great word. Yeah, it's great. Define vector r, where by definition r is the sum of x and y. Well, if we want to define a vector, that includes two things. We need to define the magnitude of the vector and the direction that it points. Okay. Now, this is a bit of a simplified case. All right, and that's for a reason. But well, with these two vectors, if we want to add them, we just got to make sure they're tip to tail. All right. So there's a tip to tail addition of x and y. Vector r, by definition, is the resultant of these. And it's a little curvy. Pay no attention to that curvy. Come on, I gotta see it better. Oh yeah, that's great. There's vector r. All right, now, on purpose, I chose these two vectors x and y to be perpendicular because if they are, well, this situation allows us to use some tools that aren't physical tools like rulers and protractors. All right, and you already have a couple of tools you could use to define vector r. And again, namely, that means to define the magnitude of r and the direction that it points. Well, the magnitude of r the length of r, well, this is a right triangle we've made out of these vectors. So we can say that the magnitude, absolute value of r squared, is the magnitude of x squared plus the magnitude of y squared. All right, or that the magnitude of vector r is the square root of the sum of the squares of the magnitudes of x and y. Right? Right. No problem. Pythagorean theorem. Right? Yeah, no problem. Great. The direction that vector r points, well, when you define the direction that any vector points, what you most typically do is, it's always an angle, and you always measure an angle that the tail of the vector makes with some reasonable reference direction. In this case, the horizontal is a reasonable reference direction. And here's, well, you're going to have to do something with trigonometry. And what I'll tell you is, again, if we're given x and y, we should strive to use something about those knowns as opposed to using a calculated answer, which could include some rounding. We might as well try to use x and y to find theta. Well, you'll notice that y is what we call the opposite side of this triangle relative to angle theta, and x is what we call the adjacent side relative to that angle. And opposite and adjacent live in the trig function tangent. So we would say that the tangent of theta is the magnitude of vector y divided by the magnitude of vector x. Or that theta, therefore, is the inverse tangent of the magnitude of y divided by the magnitude of x. And that's it. Okay, so if I gave you x and y, you could tell me everything there is to know about vector r using a couple of trigonometric tools. Agreed? Super. What if, as opposed to me telling you what vectors x and y are, I gave you vector r? Right, so here's a vector r. And that means if I give you vector r, I tell you what vector r is, that says that I've told you it's magnitude and direction. That means we know the size, the length of that vector, and it also means that we know the angle that this vector points relative to some accepted reference direction, like, say, the horizontal. All right, well, the task in a situation like this, as opposed to here, where I have two perpendicular vectors and I want to find their resultant, this task is the reverse of that. This task is, here's a vector, let's break it up into perpendicular components. Component is a fancy way of saying parts. So there are two, and only two, vector, well, that's actually not true. There are two perpendicular vectors that also happen to point along this common accepted upon set of axes that we'll use a bunch, horizontal and vertical, or x and y, or north, south, east, west. If we use that kind of standard directional orientation, there's only one set of vectors that point along those directions that could make up vector R. And so quite literally, if we want to know what we call the horizontal component of R, the question is, well, how far along this axis does vector R point? Well, it points out to there. And so I would draw this as what I call Rx. So horizontal, we call this maybe the x component of R. Or perhaps the horizontal component. Or perhaps the east component, or something like that. Right? And if we want to know the vertical or the y component, or maybe the north component, we say, well, how far along this axis does that vector point? Well, it goes out up that high. So I would draw a vector like this and call that Ry, which we would call the, don't write it over here, the y component of vector R. Yeah? It's okay? Now, as maybe some of you were saying, well, wouldn't you draw it over? I'm surprised that you didn't draw this vector over here. But it's the same vector. It doesn't matter where you draw it. I like to draw it here because I like to start all these vectors from the same place. But as you know, this vector is the same vector no matter where we put it. And there certainly is an argument that showing these vectors as part of a right triangle can be useful for us. But either way, here's R, Y. Golly geez. There you go. All right. Now the question is, how do you find those perpendicular components? Well, we already know their directions. Our Y points in the along our what we call y-axis, right? So right now we're using a coordinate system where we call that the positive x, and we call that the positive y. All right, so we know the direction of Ry. The question is, how do we find its magnitude? We know the direction of Rx. The question is, how do we find its magnitude? All right, well, here's the deal. Remember here, where I told you x and y, well, we didn't know the hypotenuse of this triangle, so we used tangent to identify the angle. All right, here we know R. The things that we don't know are Ry and Rx, so we can't use tangent because tangent has both of those in it. But if you use sine and or cosine, like for example, you could say, well, the cosine of theta is, whoops, it's not opposite, dummy, it's adjacent. over hypotenuse, that means that the cosine of theta is, Rx over R. Oh yeah, well I told you that we know, sorry, Rx and R. I told you that we know R and theta, so if I do this and say, well, multiply both sides by R, and then this goes with that, what we end up with is Rx is R cosine theta. Nice. Well, yeah, sure, why not? Keep that. So if I know the magnitude of vector R, and I know the angle that R points at, in this case, relative to a x-axis, well, this Rx is how I find the magnitude of the x component. All right. Similarly, if I do sine of theta is opposite over adjacent, that means that the sine of theta is Ry over R. And that means we end up with, if we solve for Ry, that Ry is R sine theta. All right, so now I hear some of you saying, I can hear you, can I just use law of sines? Okay, sure, whatever. This is how I do. This is how I'll teach it. There's lots of different tools you have here, but this is the way that lots of folks in our world talk about how to find vector components. All right. So, and I will tell you that you're going to use this just hundreds of times in the next couple of months. All right. We'll talk about tons of cases where maybe R is a velocity, and this is a representation. Oh, look, like in this case. All right. So maybe we say, here's an object that's shot with an initial velocity of 15 meters per second. And of course, I'd have to tell you at an angle of, I don't know, what's that look like? 22 degrees? Yeah. It's probably closer to 32 degrees. And we want to find the horizontal and vertical components of this object's initial velocity. Well, we'll do this a ton because we're going to start to look at when this thing's shot. Well, then the object will follow a parabolic trajectory like that, and blah, blah, blah. So this object's initial velocity has a huge influence on what its trajectory looks like. And so for us, it'll be real important to know, don't draw that. It'll be real important to know things like, well, how fast was this object initially moving horizontally? How fast was it initially moving vertically? And so we can draw, not a bad idea to sketch them. We don't need rulers and protractors anymore. This is the nice thing. This is what we would call V0 x. Wait, I thought it was called Rx. Well, it's called Rx if it's a part of vector R. So this is called V0 x because it's a part of vector V0. And this is called V0 y because, again, it's a part of vector V0. It's the y part. So, well, let's see. V0 x, by definition, is V0 cosine theta. Right? I'm not going to recreate the wheel. I'm not going to start by saying, well, the cosine of theta is adjacent over hypotenuse. The adjacent side is this. Blah, 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 blah. I'm just going to, boom, start right there. The faster you can start right there and buy into that and just rattle that off, the better. Okay? If you have to every time for a while, start here and then substitute and then, okay, rearrange. That's okay. It's certainly not wrong, but the faster this becomes second nature, your opportunity, your chance for success just really gets a lot bigger in the next couple of months, 2-3 months. Okay. So now we substitute V0 x is 15 meters per second times the cosine of 22 degrees. Degrees is a unit. Must be included in work that you're actually getting an answer. All right, so 15 cos 22 14 meters per second. Well, I got 13.9. Yeah, I know. There's two sig figs, right? 1, 2, 1, 2. 1, 2. The vertical component, V naught y, is V naught sine theta. V naught y is 15 meters per second times the sine of 22 degrees. V naught y is 15 sine 22. 5.6 meters per second. Easy peasy, right? Can I just use law of sines? Whatever you want, man. This is the way I'm gonna do it every single time I talk about how to find components. Okay. Here's another just sort of no numbers here, but let's say that we have two forces, F1 and F2, and we want to do a qualitative comparison. Now, here's what's important. What's important is that what I do is take this one, clone, and then flip left and right. So it's just a reflection of F1. They're symmetrical about that axis. Agreed? And what that means is, how do these two things compare? Well, it means that they have the same exact, here's F1y, F2y. And those two components are exactly the same thing. Those vectors are equal. Sure, it makes sense, right? They both point up the same amount. Here is F1x, and here is F2x. And those are not the same vector. They are alike. They are alike in that this vector and that vector are the same size, which is to say they have the same magnitude, but they point in opposite directions. So the phrase that I use to describe these is equal and opposite, which means their magnitudes are equal, their directions are opposite. So the best way to talk about these is to say that F1x, well, is the same size as F2x, except points in the opposite direction. Right? Kind of like an object that's shot upward at a speed v0 and comes back downward and has a speed v that's equal to negative v0. Right? These two vectors are equal. You get it. Equal and opposite. All right? But the big deal here is that we have to, just like we've been doing for the last 3 weeks or so, is we have to use sine to denote direction. Okay? So if F2x was like 30 newtons, the unit of force, then F1x would be negative 30 newtons, or 30 newtons left. Okay? So that's a look at what we call vector components. You need to be able to do the following. You need to be able to, I'll just go here. You must I'll type. It'll be neater. Things you must be able to do. How about right here? Draw reasonably accurate representations of the components of any vector along perpendicular axes. Which is to say that if there's a vector that I show you like that, you need to be able to say, well, it's got a downward component about that long. It's got a horizontal component about that long. Those are reasonably accurate. These are not reasonably accurate. All right, that one points, this it goes down about that far, and it goes to the left about that far. But it's completely not reasonably accurate. No good. Yay. So that's one thing you must be able to do. And two is let's say two, calculate the magnitude of each component of a given vector. Which is to say that if, well, yeah, there's Rx, or your Regents reference table says any old vector A, any vector A's x component is A cos theta. Any old vector Y or A has a y component that's A sine theta. You just need to be able to do that. All right, those are the big two things for now. You can or you can't, but you must. Okay? Okay, kiddos. See you tomorrow.